Hi, I'm Sean Moran with ACC GIS, and our topic today is vector proximity analysis. Now, this topic kicks off Intermediate GIS Competency 2, where we learn how to create, analyze, and present vector GIS data. When performing vector analysis, rarely is there one approach. Our methodology is often determined by the question being posed and the data available to inform our analysis, as well as the client's expectations on how we'll present our findings. So while the analytical process starts with a question, our analysis often depends on client expectations, available resources, and a combination of GIS tools that include vector proximity analysis. Site selection and feasibility analyses exemplify this approach. They're pre-designed assessments to determine the suitability and appropriateness of a project as it relates to a particular site. These studies consist of inventoried site data that are overlaid and analyzed to identify site opportunities and constraints. It is one of the most critical steps to producing a functional, aesthetic, and cost-effective design, and these analyses often employ a combination of GIS tools, including vector proximity analysis. Let's take a look at a site searching and selection video by UK planning and design consulting firm Barton Wilmore. It uses the analytical process in GIS to identify sites for oil and gas exploration. Now, one thing I like about this visualization is that it shows the multiple stages or phases associated with site selection. In this example, they start at a national level using blocks available for energy exploration and production, along with major transportation networks. This allows them to target the next stage of the site selection analysis on specific regions. At the regional level, they're iterating through the analytical process again. The question now is less about available leases supported by transportation networks and more about how the leases identified in stage one are constrained by the physical and natural environments, including wetlands, sites of special scientific interest, national parks, conservation areas, special protection areas, which are all merged into a single all-constrained land layer that allows them to identify opportunity areas. Stage 3 presents a more detailed local analysis. Again, the focus of the site selection analysis has become more refined on a specific locale and the physical and natural constraints, including vector data sets like buildings, open space, flood zones, infrastructure, and raster data sets like elevation, and slope. The fourth and final stage uses high-resolution data like elevation, vegetation, roadways, parcels, and ortho imagery to design the final layout of the site. While this particular analysis combined a number of different data and analysis types, you can see that proximity analysis plays an important role in site selection. Our objective is to create accurate vector GIS data through proximity analysis. And by the end of this topic, you should be able to differentiate between geodesic and planar measurements, measure feature geometry and classify by attribute, describe different vector proximity spatial relationships, list and describe different vector proximity geoprocessing tools, explain what the geoprocessing framework is, and you'll perform a site selection analysis using vector proximity tools. Now this slide is from your geoanalytics lecture where we discussed using GIS to analyze geospatial data. Over the next several weeks, we're going to be discussing geographic vector data, features, clusters, and bins, and how to utilize that data format to inform your analysis, including methods like measure, classify, query, proximity, overlay, connectivity, and custom, using ArcGIS Pro and ArcGIS Online. This week, we'll focus on vector analysis methods, including measure, classify, query, and proximity. Measure, of course, is where we calculate geometric properties, summarize statistics, or geostatistically describe features. Classify is where we group features by unique values, range, or location. Proximity query is where we search and retrieve tabular records and geographic features. And proximity analysis, where we analyze relationships between nearby features. Now, before we discuss different analytical approaches for measuring data, we need to understand that our metric and method will affect our measurement. For example, different types of metrics include Euclidean, Manhattan or raster, and network will measure different distances between point A and point B. In the example below, a Euclidean or straight line measurement measures as 6 miles between point A and point B, shown as the green dashed line in the image. Manhattan or raster is a measurement measured on a grid. Manhattan is named after the street grid in Manhattan, in which you would have to go over a block, up a block, over several blocks, up a block, and over a block to get from point A to point B, which in this example is 8 miles and is longer than the straight line distance. Another metric is a network distance, which is measured along a street network. So for example, when you use Google Maps and you measure the distance between point A and point B, it measures the distance along the roads, not a Euclidean or Manhattan distance. And in this example, the network distance is 7 miles. Now, while we've got different distances for the different types of metrics, not one metric is better than another. It just depends on what you're trying to accomplish. You need to select the appropriate metric. The method will also affect your measurement. Methods include geodesic and planar. Geodesic is measured on a sphere, and planar is measured on a plane, which is a projected and stretched sphere. That's why when you look at the example below, you can see that the geodesic measurement from point A to point B is 5 miles, and the planar measurement is 6 miles. Even though the planar measurement looks like it's shorter, the planar measurement is on a projected and stretched sphere, so it's actually longer than the geodesic measurement. To help you visualize the difference between planar and geodesic measurements, I'm recreating a map published in 2003 by The Economist alongside an article about North Korean missile range. The map incorrectly showed the maximum 10,000 kilometer range of North Korea's most advanced missile. Let's recreate the map and resulting error using planar and geodesic measurements. We'll start by adding a North Korean launch site to our map. I'm going to go ahead and pan over. There it is, located in North Korea. And I'm going to update the symbology to make the launch site look a little more menacing. Now I need to check the coordinate system for the map view. So I'm going to right click on the map in the contents pane and select properties. And I want to confirm that I'm using a projected coordinate system, and I am. This is what's known as the Google coordinate system. and it's a projected coordinate system. But I'm also going to enable wrapping around the date line so I can see across the Pacific Ocean to the United States. All right, now I'm ready to create my buffers. We'll click on the Analysis ribbon, and then in the Tools gallery, I'm going to select Buffer. I'm going to set my input features in the Buffer Geoprocessing tool as North Korea launch site. My output feature class, I'm going to name as North_Korea_ 10K missile_range planar. And then I'm going to set my distance as 10,000 and my linear unit as kilometers. Now I need to click on the environments panel and confirm that the output coordinate system is set to my projected coordinate system, which I'm going to set it the same as my map. And then go back to parameters, and under method, I want to make sure that I have planar selected, and go ahead and click run. Now this is how the economist created the missile range. Now let's recreate the missile range utilizing the correct approach, which is geodesic. So I'm going to rename my output feature class as geodesic, and then switch my method from planar to geodesic, and then click run. Now, as you can see, there's a big difference between the two. One threatens the continental United States, one does not, but they both were buffered using 10,000 kilometers. So let's go ahead and close the geoprocessing pane, and now let's measure the difference between the two buffers. So I'm going to go to the map ribbon and click on the measure dropdown and select measure distance. And I want to go ahead and recenter my map and confirm that my snapping is turned on and that I've enabled point and edge snapping. And then now I'm going to change my method to planar and units to kilometers. And then I'm going to snap to the North Korean launch site and to the edge of the planar buffer. Notice it says 10,000 kilometers and the geodesic one says 15,000. But the missile doesn't travel on a straight line across a flat plane. The missile travels around the sphere of the Earth. And so this map is distorted and stretched onto a flat plane. So if I change my measuring distance to geodesic and then select the launch site and go to the edge of the planar, notice that it's just a little over 7,000 kilometers. And now I go to the edge of the geodesic and it's 10,000 kilometers, which is a big difference for the United States as far as the threat of a North Korean missile that travels 10,000 kilometers. So it's important that you select the right measuring metric and method when you perform analysis. If you're going to do global analysis, you want to use geodesic measurements. If you're going to do local analysis, you want to use planar measurements.